here are a few examples of determining whether or not the given functions are rational functions. So if you recall, rational functions are in the form p of x over q of x, where p and q are polynomials, where the powers are counting numbers. There's no x's, there's no square roots, that kind of thing. So if we look at this first one, we'll go here. We have x squared plus 2 over x squared minus 1. The top is a polynomial of degree 2. The bottom is a polynomial also of degree 2. So this first one, yes, it's rational, and it's already in the form that we need it to be of p of x over q of x. There's nothing to really do here for that one. All right, the second one here, 4 to the x plus 3 divided by 3 to the x minus 1. The fact that x appears in the exponent makes this an exponential function. Those are not polynomials. This will not be able to be expressed as a rational function. That's all you have to put for that one, is that it's not. All right, for this third one, you see a lot of terms that have polynomial qualities, like an x squared, the constants, the x. So this one has potential. And so what we want to try to do, though, is we have to get it as to one single polynomial over another single polynomial. So this will involve creating common denominators. So I'll multiply x to the fraction on the left, 2 to the fraction on the right. I get an x cubed over 2x, and then I get a 2 over 2x. So when I add across the top, I get x cubed plus 2 all over 2x, where x cubed plus 2 is a polynomial and 2x is also a polynomial. So our rational form of that problem is x cubed plus 2 over 2x. So yeah, that one's rational, a rational function. A couple more. So this fourth example here, the square root of x is x to a 1/2 power, and you can't have a fractional power in a polynomial. The power for a polynomial has to be a positive integer, like a counting number, 1, 2, 3, 4, or even a constant. And because that's a 1/2 power, this is not going to be able to be expressed as a rational function. So it's just not a rational function. All right, so for this fifth example, a lot of polynomial type qualities. The powers are whole counting numbers, even though I think you can simplify a little bit on the first one. They do need to have common denominators, and so for now, if you want to, you can simplify. You may lose some zeros, so if we left it, the 2x squared needs 3 more, so that you have that 6, and the 6 needs an x squared. So you have 3x cubed over 6x squared plus x squared over 6x squared, and then that gives you 3x cubed plus x squared over 6x squared. Those are polynomials, but the reality for this problem is the top you can factor out x squared, and you're left with 3x plus 1, and then that will cancel with the x squared on the bottom. So that will give you 3x plus 1 over 6, which is going to be linear, but the fact that we left it as a polynomial up top and a polynomial on the bottom, you can't simplify the 3 and the 6 because the 3x has a plus 1 added to it, but that is going to end up being a line. But in the p of x, where p of x is a polynomial, q of x is a polynomial, that is in that form of p over q. All right. For this last example, you've got an x, and then what is an actual rational function chunk here at the end, but we need to make it a single polynomial over another one. So the single x will just give the denominator because it doesn't have one. So we can just put 4x minus 3 on the bottom, multiply 4x minus 3 on the top. So the top becomes 4x squared minus 3x over 4x minus 3. And then you have 2x plus 1 over 4x minus 3. And then we can add across the top now that we have a common denominator. So I get 4x squared plus 3x, or negative 3x plus 2x is going to be a negative x plus 1. And that's over 4x minus 3. And you can try to factor the top, but nothing's going to have, the factors are not going to include 4x minus 3 because this is a 1 here at the end. So you have a polynomial up top, you have a polynomial in the denominator, and that would be the polynomial form, the rational function form for this given example.